Welcome to lesson 5.9 on polarity. So, a reminder to title your notes and that these are the 3.5 things you will learn by the end of this video. Okay, so far during the second half of Unit 5, we've talked about covalent molecules, so molecules that are only made up of nonmetals, how to find their 2D structure through Lewis dot structures, and how to use Vesper theory to find their 3D shape. Right? And if you're thinking about viruses or foods that taste good together, right? Let's talk about viruses first. All viruses have a 3D shaped molecule because we live in the 3D world that attach to our cells. And specifically on the outside of our cell membrane, we have these receptor sites or other molecules that kind of act as a lock where these attachment sites fit into, and this allows the virus to enter our cell and replicate millions and millions of other viruses until they can't replicate anymore and they'll burst out of our cell and infect our other cells. Right? And you might wonder, why in the world would our body even have these receptor sites or receptor molecules in the first place? And that's because they're not made for the virus. They're often made for things that our cell needs, like different amino acids or other molecules or ions that we might need, so on and so forth. But the virus has mutated to hack in to these receptor sites and allowed itself to get in. So basically, it's like a fake key copy to get into someone else's house. Right? But there's kind of one more thing that the virus needs to get inside our cell besides just the correct molecular shape or 3D shape. And that thing happens to be called polarity. So in this video, we're going to go over what polarity is, and when we come back from break, we're going to talk about how this relates to viruses or flavors of things, right? So polarity in general describes the uneven distribution of electrons, creating an overall charge in the molecule. So basically what happens is if I have an uneven sharing of electrons, and remember that electrons are negative, right? I'll essentially end up with a molecule that might be slightly negative on one side, but a little more positive on the other, right? So if you recall in Zoom class, you might notice some weird things happen if there's a slight difference or an overall charge in the molecule. So in general, a polar molecule is a molecule that has an uneven distribution of electrons, right? Basically, what that means is one part of the molecule has more electrons than the other, right? They're not being shared evenly. On the other hand, nonpolar molecules have an even distribution of electrons, right? So in this case, the electrons are shared evenly between both atoms or both elements. And based off of that, these two definitions, can you tell which molecule is polar and which is nonpolar? Go ahead and pause the video and see if you can figure this out on your own. Okay, did you take your guess? Let's check it out. Okay, so for me, remember that polar means uneven electrons, nonpolar, even electrons. So when I try to solve this, in my head, I kind of look at the top half and the bottom half. And then I look at the left side and the right side, and I compare both sides to see if they are symmetrical. So checking the left and the right and top and the bottom. And if they are symmetrical, to me, that is non-polar. right? So in this case, the molecule is, excuse me. So in this case, the molecule is symmetrical both left and right, meaning they're the same left and right, and top and bottom, right? So this shows me that it is non-polar. The other method, right? So if I do this again, splitting it left and right hand side, notice that they're not even on both sides, and Cl has more electrons or lone pairs around Cl than H. Right. But if I split it top to bottom, it is symmetrical. So if it's not symmetrical left to right, right, even though it's symmetrical top to bottom, this is considered polar. Right. So what we just kind of went over is an informal method of identifying whether a molecule is polar or nonpolar when there's only two elements. So oftentimes we don't teach it like this in chemistry because there is a slightly more formal way, but this is what I like to do because to me it's a little bit faster and I can automatically see it if I can see the molecule. Right. So let's go over how we would do this formally in chemistry. I also forgot to mention to make sure to write down the definitions in red, and this method, if you prefer it, you can always jump back to this method if you prefer it, but I'm going to show you a different method in the next slide. Okay, so let's go over the formal method or the regular way of figuring out whether a molecule is polar or nonpolar when there's only two elements, right? So essentially what we need to do is to find the electronegativity difference of both elements, right? And remember, electronegativity is how strongly an element or an atom attracts electrons, right? So to find the electronegativity difference in step A, we first need to find the electronegativity numbers for the molecule Na and Cl. It doesn't really matter which one goes first, so using my electronegativity table, and this I will provide for you, the electronegativity number, or how strongly Na wants electrons, is 0.9. Cl, on the other hand, is here, and its electronegativity number is 3.0. So to find the difference, I'm just going to subtract. And I'm always going to take the absolute value of this number, or the positive number. So 9 minus 3.0 will be negative 2.1. But since we're taking the absolute value, it's going to be 2.1. Right. So because this is 2.1, my next step is to check the scale, so this electronegativity difference scale, in order to see which range it falls in. So the larger the number, the more uneven the electrons are being shared, and the closer the number is to zero, the more evenly the electrons are being shared. So based off of this scale, right, any number that is greater than 0.4 is considered polar, right? If you want to get more detailed about it, right, electrons that gain or lose, excuse me, elements that gain or lose electrons are called ionic bonds because they're not being shared very evenly at all. So these are the most polar, right? And then if they're kind of being shared unevenly, then you have a polar covalent bond. But in general, if it falls anywhere within this range of greater than 0.4, it is essentially polar. And if it's 0.4 or less, we call this nonpolar. Right. So since we got an electronegativity difference of 2.1, we can call this either polar, or if we want to be more specific, it is a polar bond that is considered ionic, right? Meaning that these electrons aren't really being shared evenly at all. They're kind of almost being given away to one of the elements. Either answer kind of describes the bond, right? So this would be polar or ionic. And if we double check the first method, where I just had you draw the Lewis dot structures, let's do this in blue, right? If I draw out the Lewis structure of NaCl, it would look something like this. And if I split it in half this way, right? My left side and my right side are not even. So I can tell that it's also going to be polar. Right? So both these methods are pretty reliable, whichever you happen to prefer. Do recognize that in AP Chemistry, if you plan on taking AP Chemistry in your future, that you will need to know how to solve it this way. Okay, what if I have a slightly complicated molecule, a molecule where there's more than two elements? So how do we identify whether a molecule is polar or nonpolar when there's more than two elements? Right, so here's an example of how to solve this. So determine whether CH4 is polar or nonpolar. Right, so I've created a flow chart of all of the steps because it's kind of a little more tricky. Right, so starting at the top, step number 1, draw the Lewis dot structure and ask yourself, is it symmetrical? So let's do step 1 in blue. Right, so I've already drawn the Lewis dot structure for CH4, going across top and bottom and left and right. And if I look at it, symmetrical, right? So yes, it's symmetrical, top with bottom and left to right. Therefore, it is nonpolar. So CH4 is going to be nonpolar. Super straightforward, right? Okay, so let's try a harder example where it's not symmetrical. Okay, same flowcharts, different problem. So here in this example, determine whether PBr3 is polar or nonpolar. So we drew the Lewis dot structure. Let's check if it's symmetrical. So drawing a line left to right, right? So my left side is pretty much the same as my right side, right? So therefore it's symmetrical left to right. But if I draw a line going across, the top half and the bottom half are not symmetrical. So in this case, after completing step 1, we now know that it's not symmetrical. So at this point, I need to do something a little bit extra. So I've erased the dotted lines just to make things a little more clear, right? But we've already determined that it's not symmetrical. So our next step is going to be find the electronegativity number of each element and draw arrows along the bond lines. So let's do that next. So we need to find the electronegativity number for Br and for P. All right, so going on to here, looking for the element P or phosphorus. It is here. So it's 2.1 and Br is 2.8. So let's go back to the other slide and write that down. So 2.1 is electronegativity of P and Br is 2.8. Right. And then my next step is going to be draw the arrows along the bond lines. And note that I say afterwards that arrows point towards the elements with the higher electronegativity. So I'm going to follow this bond line between P and Br, and my arrow is always going to point towards the elements or the atom with the higher electronegativity number, whichever one wants the electrons more. Right. So notice that I draw kind of a vertical line here, and this arrow is what we call a dipole. So a dipole, let me write it on the side here. Or a dipole arrow represents so a dipole is essentially an arrow that represents where the electrons are congregating or congregates, basically where they go together, causing either a partial positive or negative charge, right? So the tip of the arrow where it's pointing is where it's more negative. And to show and remind other chemists that this is the positive end, if I just focus on this part, it kind of looks like a plus sign, right? So this is just to remind you that this is the plus part or the positively charged part of the molecule. And the arrow where it's pointing is the negatively charged end of the molecule. All right. So following this bond line between P and Br, I'm going to draw an arrow facing points 8. Right? So this dipole is going to go this way, and this dipole is going to point down. Right? So now that I have all the dipoles drawn, notice that they all follow the same direction as the bond line. Right? So now you're going to ask yourself, do all the dipoles cancel out or face away from each other? Well, if I look at this, I'm going to do this part in green. Right. So the one pointing left and the one pointing right will cancel out and face away from each other. So yes, this one does. But this dipole pointing down, all the electrons are down here, but there's no dipole pointing up to cancel this out. So that means that even though all of these electrons are kind of pulling together over here on the left and the rights, they'll balance each other out. On the other hand, there's nothing to balance this electron hog here, Br, that has all the electrons. So in this case, there's nothing to cancel this dipole or this arrow or all the electrons down here. right? If there was one up here, then it would cancel out. But in this case, this one does not get canceled out. So in this case, no, they don't cancel out. So therefore, it's polar. So therefore, this molecule is going to be polar. Normally, this is much faster. I just went a little bit long because I was explaining what a dipole is and going over in detail with this chart. Right, so I would definitely have this flow chart written down and definitely just know what a dipole represents. Right. So at this point, you should be able to complete some of the practice problems on your own.